It appears that the information about what fell in is lost, apart from the total amount of mass and the amount of rotation. But if information is lost, this raises a serious problem that strikes at the heart of our understanding of science.
Today, everyone knows there are strange objects in space where anything that falls in is gone forever. Black holes. Indeed, it is believed that any object that falls into a black hole disappears without a trace, with no way back. Entire stars can vanish in black holes, let alone planets like ours, which could easily be swallowed up along with all the knowledge humanity has ever accumulated. Of course, that's a hypothetical scenario. But let's suppose it happened. What would become of all the information humanity has gathered? As solutions to Einstein's equations show, a black hole is described by only 3 parameters, regardless of what falls into it: mass, angular momentum, and charge. So, all of humanity's exabytes of information vanish, and we are left with only 3 numbers. Yet, the laws of conservation tell us that if the full description of a system is known at a given moment, then its past can be reconstructed and its future predicted. The information about the system is not lost. But with a black hole, we can no longer restore anything. All we are left with are those 3 numbers. So, where does the information disappear? Where did the whole of the Bagel that fell into the black hole disappear? Is it even possible to fall into a black hole? And how to make sure that our planet, along with the Sun and all mankind, never gets into it?
On June 18, 1962, a research rocket named Aerobee was launched from the White Sands Proving Ground in New Mexico. It was an American 2-stage suborbital rocket designed for experiments in the upper layers of the atmosphere. The scientific payload of this rocket consisted of Geiger-Miller gas counters with thin beryllium windows for detecting X-ray radiation in the wavelength range from 2 to 8 angstroms. After launch, before reaching its apogee, protective shutters opened, and the detectors began scanning the sky in spiral stripes as the rocket rotated. The data was transmitted to Earth in real time. This flight marked the beginning of X-ray astronomy. The initiator of this research was the American physicist Riccardo Giacconi. Giacconi and his team set an ambitious goal: to create a map of the entire sky in X-rays. Launches of these rockets continued until the late 1960s. Even from the earliest flights, scientists detected a bright X-ray source as well as diffuse background radiation. In 1964, 8 more sources were identified, including a strong one known as Cygnus X-1. Its nature was unclear. Perhaps it was a hypothetical black hole that had previously existed only in theory? Unfortunately, the Aerobee's suborbital flight lasted less than 6 minutes, which did not allow for detailed study. Scientists around the world debated fiercely about the nature of the newly discovered X-ray sources. The arguments grew so intense that they even led to a famous bet. In 1974, two outstanding physicists, Stephen Hawking and Kip Thorne, made a wager. Hawking argued that Cygnus X-1 was not a black hole, while Thorne insisted that it was. To resolve these debates, precise measurements were needed, something only a true space-based observatory could achieve. And just a little earlier, before the entertaining dispute between scientists, a turning event in the development of space astronomy took place, which later helped in solving the problem. Namely, December 12, 1970, when the satellite Uhuru was launched from the San Marco offshore platform near the coast of Kenya, aboard a Scout launch vehicle. Its launch was timed to coincide with Kenya's Independence Day, and the satellite's name, Uhuru, means freedom in Swahili. From that day, the world had its first dedicated X-ray space observatory. Uhuru operated in orbit for 3 full years. Despite weighing only 140 kilograms, it opened an entirely new chapter in the exploration of space. During its mission, the satellite surveyed the entire sky in X-rays, creating catalogs containing hundreds of sources. Special attention was given to Cygnus X-1. The satellite recorded rapid variations in X-ray intensity, indicating that the source must be extremely compact, no more than about 100,000 kilometers in size. This is far too small for an ordinary star, but exactly what would be expected for a black hole. Using two methods, measurements of companion star oscillations and observations of the X-ray variability, scientists confirmed that the second object in the Cygnus X-1 binary system is invisible through optical telescopes. It reveals itself only through its gravitational influence and its X-ray emission. These are the defining signs of a black hole. This made Cygnus X-1 the strongest candidate to become the first widely recognized black hole. Only in 1990 did Stephen Hawking admit his defeat and paid Kip Thorne the agreed prize, a 1-year subscription to Penthouse magazine. The term black hole first appeared in print in 1964, thanks to Anne Ewing, a science journalist from Science Newsletter. In an article titled "Black Holes in Space," she firstly used the term in popular science. At that time, scientists called such objects as frozen stars or gravitationally collapsed objects, but those expressions were awkward. The name black hole became officially accepted in 1967. During a lecture at the Goddard Institute for Space Studies in New York, the American theoretical physicist John Wheeler, known for his talent in crafting vivid and memorable scientific language, expressed a desire to use a shorter and more apt name instead of fixed stars. According to one account, someone in the audience called out, "How about black hole?" Wheeler liked the suggestion, and from then on, the term entered scientific vocabulary.
Black holes are one of only a fairly small number of cases in the history of science in which a theory was developed in great detail as a mathematical model before there was any evidence from observations that it was correct. Indeed, this used to be the main argument of opponents of black holes. How could one believe in objects for which the only evidence was calculations based on the dubious theory of general relativity?
So, to answer the question posed at the beginning of the film, where does the information disappear from objects falling into a black hole? Simply knowing their name and fact of their existence is not enough. As we've just seen, thanks to the data from the Uhuru X-ray Observatory, theoretical predictions have been confirmed. But what could an object with such a strange name, a black hole, actually look like?
The first image of a black hole was created in 1978 by the French astrophysicist Jean-Pierre Luminet. He modeled the gravitational field of a hypothetical black hole and its accretion disk. The work was performed using one of the early transistor-based IBM computers. The IBM 7040 model was installed at the Paris Moudon Observatory. Where Luminet worked as an astrophysicist and researcher. The computer he used had neither a keyboard nor a display, as we are accustomed to today. Its memory capacity was less than 1 megabyte, thousands of times smaller than that of a modern smartphone. And programs were entered using punch cards. Luminet wrote code that calculated the trajectories of light rays and the intensity of radiation emitted by the accretion disk. The results of his calculations were printed as columns of numbers. Based on these printouts, Luminet manually created the world's first visual representation of a black hole, transferring the numerical data onto paper, dot by dot using ink and a rapidograph technical drawing pen.
I finished the whole thing over 2 evenings. I drew around 10,000 black dots with a density proportional to the light flux. In other words, I took what was originally a negative and turned it into a positive image and published it. So it was a black and white image, because in fact it was what we call a bolometric image. That is, it represented an integration over all possible and conceivable wavelengths. It wasn't a radio image, or an optical one, or anything like that, so there was no actual color to work with. In any case, even today, when we use color in such images, we still use false colors. And so, I had the opportunity to create this model, which at the time seemed natural to me. It didn't seem extraordinary in any way. Then, in 2019, the Event Horizon Telescope presented the first telescopic image, including a supplementary view, of the presumed supermassive black hole at the center of galaxy M87, surrounded by a glowing corona, which was interpreted as an accretion disk with hotspots, and so on. Yes, and the second part of the question concerns both the difficulty and the similarity with the images from 2000 and 2019. First of all, you may recall that at the end of my 1979 paper, in the final sentence, I wrote that this was, of course, a theoretical calculation, and that if someday we were able to obtain such an image through observation, it would necessarily imply a high resolution or sharp visual acuity, which at the time was unimaginable. And I also mentioned that the ideal object would be a supermassive black hole, the existence of which had just begun to be suspected at the very center of the galaxy M87. I never imagined this could happen within my lifetime, let alone that M87 would actually be the first. Why? Simply because M87 contains a supermassive black hole whose mass is 5 to 6 billion times that of the Sun. And in terms of its apparent size in the sky, it is the largest, or rather the least small in the sky. Its projection on the sky is roughly equivalent to the size of a €1 coin placed on the surface of the Moon. At the time, I didn't yet know that radio wave observations made it possible to perform what's known as interferometry. That is, to link radio telescopes located in different parts of the world and use them in a mode called Very Long Baseline Interferometry, VLBI, effectively creating the equivalent of a single radio telescope the size of the entire network. And it was only much later that I learned that already in the 2000s, dozens of researchers from around the world, some of whom had been partly inspired by my 1978 to 1979 paper, began to ask a bold question: could a global network be created which they named the Event Horizon Telescope? The event horizon is the technical term for the surface of a black hole, to achieve extremely high resolution in the radio band at a precisely defined wavelength. The goal: to reach the capability to observe something as small as a coin placed on the surface of the moon while observing it from Earth. There were only two black holes suitable for this kind of observation, Messier 87, and the other is the black hole believed to be at the center of our own galaxy. Although when I wrote my article, this second one wasn't yet being discussed. The idea of observing it only emerged in the 1990s. It's much less massive, but also much closer, and those two factors balance each other out. So in terms of its apparent size against the background of the sky, it ends up occupying roughly the same angular size. The Event Horizon Telescope was created specifically to observe these two black holes. They were finally observed in 2017. So the first image, after numerical simulations and extremely complex data analysis, showed the black hole in Messier 87. And 2 years later, since it was somewhat more complex, an image was also obtained of the galactic black hole Sagittarius A star. So now we have two reconstructions. It's important to note that when we talk about telescope images, listeners or viewers might picture something like the beautiful photographs captured by the James Webb Space Telescope. But in this case, we're dealing with extremely complex reconstructions based on massive amounts of data. We're talking about petabytes of information collected by each radio telescope in the network data that must be integrated using advanced computational algorithms. There are several possible image reconstructions, and these are compared with theoretical models, like the ones I created 40 years ago, but now far more sophisticated, with many more parameters and powered by supercomputers. What we ultimately get is the so-called photograph of a black hole, which in reality isn't a true photograph at all, but a reconstruction. And in conclusion, I won't go on too long, but regarding this match, indeed, when we first saw those images, I said, yes, we've reached the Luminay's calculations. This is incredible.
So, what did Lumina draw? We obtain data about celestial objects from the radiation they emit. Unlike stars, black holes emit nothing. Well, almost nothing. They absorb. After the launch of the space-based X-ray observatory by Professor Gianconi's team, it was discovered that X-ray sources are components of binary star systems. In these stellar pairs, alongside the X-ray source, there is an ordinary optical star. This star loses matter, which falls onto a compact object. The infalling matter gathers into a disk, rapidly rotating around the object like a satellite. This disk emits energy. It is precisely this disk that allows us to detect the otherwise invisible compact object, a black hole. Most of this energy is emitted in the X-ray range. This region, where the matter spiraling into the black hole rotates, is what Lumina depicted in his visualization. In other words, this region is called the accretion zone. This is the very image often used in popular science magazines when discussing black holes. But what does all this have to do with a planet falling into a black hole, along with all its bagels, bakers, and wheat fields?
Philosophical Transactions of the Royal Society of London is the oldest scientific journal in the world, first published in 1665. Its pages have featured the works of Isaac Newton, Robert Hooke, Antony van Leeuwenhoek, Charles Darwin, and many other great scientists. In the 74th volume, released in 1784, there was published a letter with a long title, On the Means of Discovering the Distance, Magnitude, and so on of the Fixed Stars, in consequence of the diminution of the velocity of their light, in case such a diminution should be found to take place in any of them, and such other data should be procured from observations as would be farther necessary for that purpose. The author of that letter was John Michell, a scholar who spent 20 years at Cambridge, where he taught classical languages and various scientific disciplines and conducted research on magnetism and earthquakes. Later, he became the rural pastor of St. Michael and All Angels Church in Thornhill, Yorkshire. The life of an average English country clergyman at that time was unhurried, receiving tithes from peasants, income from rented land, and fees for performing church rites. Many clergymen could afford to live in leisure, but not John Michell, for whom God and science were not separated. He chose to devote his life to serving both people and knowledge. He also studied binary stars, built a torsion balance, and conducted magnetic research, but his most important contribution was the prediction of the existence of dark stars. Michell calculated that if the radius of a sphere with the density of the Sun were 500 times greater than the radius of the Sun, then the escape velocity from its surface would be equal to or greater than the speed of light. In that case, all the light emitted by such a body would be drawn back to it by its own gravity. Such a star would be invisible to a distant observer. Michell called these objects dark stars. This was the first known prediction of what we now call black holes. 131 years after Michell's publication, on December 2, 1915, an article titled Die Feldgleichungen der Gravitation, The Field Equations of Gravitation, Proceedings of the Prussian Academy of Sciences. The author was Albert Einstein. The article represented the culmination of his intellectual journey. It contained the very field equations that form the core of the general theory of relativity. Their essence can be expressed as follows: mass and energy curve spacetime, and this curvature is what we perceive as gravity. In the publication, Einstein demonstrated how his new theory elegantly explained the observed precession of Mercury's perihelion, a long-standing mystery unresolved by Newtonian physics. However, the equations themselves were extraordinarily complex, a system of 10 non-linear partial differential equations. Einstein believed that an exact solution was unlikely to be found in the near future, and he relied on approximate methods in his own calculations. Meanwhile, World War I was underway. After early advances on the Eastern Front and the capture of Vilna, the 10th Army, in which artillery officer Karl Schwarzschild served, became bogged down in brutal fighting. Long months of trench warfare followed, and the artillerymen sometimes had idle hours. During this time, Schwarzschild came across the issue of the proceedings that contained Einstein's article. Being an exceptional astrophysicist and working under the harsh conditions of war, Schwarzschild accomplished in just a few weeks what Einstein himself had considered nearly impossible for the foreseeable future. He found the first exact solution to the gravitational field equations around a spherical mass. This was not merely a result, but a genuine scientific breakthrough, giving the new theory its first concrete mathematical form. On December 22, 1915, Schwarzschild sent his solution to Einstein. In his letter from the front, he wrote, "As you see, war has been kind to me. allowing me, despite the heavy artillery fire nearby, to take this walk into the land of your ideas. Einstein was deeply impressed, as Schwarzschild's solution provided an exact form of the equations that Einstein himself had only been solving approximately, including for the precession of Mercury's orbit. In his reply of January 9, 1916, Einstein wrote, "I have read your paper with the greatest interest." He personally presented Schwarzschild's paper on the gravitational field of a point mass in Einstein's theory at a meeting of the Prussian Academy of Sciences in January 1916. This was the first exact solution to Einstein's equations describing the gravitational field around a single spherical object, a star or planet. It showed that for any mass there exists a critical radius, now known as the Schwarzschild radius. This radius marks a boundary of no return, later called the event horizon. If an object is compressed below this radius, its gravitational pull becomes so strong that nothing, not even light, can escape. Thus, Michell imagined that light, like a stone thrown upward, tries to escape a gravitational well, but lacks the necessary speed. Schwarzschild demonstrated that beyond this boundary, the very direction outwards ceases to exist. The radius calculated by John Michell 131 years earlier, and the Schwarzschild radius derived from Einstein's equations turn out to be identical, expressed by the same formula. This is how the mathematical birth of the concept of the black hole occurred.
The term event horizon turned out to be a very apt name for that region of space-time from which nothing can escape. It is truly a horizon beyond which all events disappear from view. It marks the point of no return, where gravity becomes so strong that even light itself cannot escape. Sometimes the event horizon surrounding a black hole is referred to as the black hole's surface. According to modern scientific understanding, to create such an object, it is enough to compress a certain amount of matter into a limited area of spacetime. Beyond that, no one knows what happens inside. That matter disappears behind the event horizon. Scientists put forward different concepts, that beyond this horizon, there could be a wormhole to another region of space, or even a singularity, a point from which the universe itself may originate. We will talk more about what's actually inside a black hole later. For now, let's focus on its boundary. Stephen Hawking suggested that this boundary might constantly emit particles, a process that would eventually cause a black hole to disappear. And with it, all the information it had absorbed throughout its existence would vanish, including the data about our Bagel possibly dropped by a cosmic baker flying by in a rocket.
I found, to my surprise and annoyance, that even black holes are not black. Quantum theory implies that particles can leak out of a black hole. They appear to be emitted from the region just outside the horizon of the black hole. At first, I was very skeptical about the idea. I thought that maybe the calculation was just a coincidence or an artifact of the approximation I was using. But the more I thought about it, the more it seemed inevitable.
While thinking through this problem, Hawking carried out a series of mathematical calculations that led to an unexpected result. Black holes, even non-rotating ones, must emit particles due to quantum effects near the event horizon. This process is related to a phenomenon known as virtual particle pair creation. According to quantum field theory, pairs of particles and antiparticles are constantly appearing and annihilating in the vacuum. If such a pair forms near the event horizon, one particle may fall into the black hole while the other escapes into space. producing the effect of radiation. In this process, the black hole loses energy and therefore mass, which leads to its gradual evaporation. Hawking spent several months trying to find a mistake in his calculations. He feared that if he published such a paradoxical result, and it turned out to be wrong, he would make himself a laughingstock. But the more he thought about it, the more convinced he became that his result was correct. He realized that the creation of virtual particle pairs at the boundary of the event horizon, with one particle falling in and the other escaping outward, provided a physically consistent mechanism. Finally, in early 1974, he presented his conclusions at a conference at the Rutherford Appleton Laboratory. His report had the effect of an exploding bomb. The session chair called his presentation nonsense. At first, nearly the entire scientific community rejected the idea. However, when physicists independently checked Hawking's calculations, they were forced to admit that he was right.
So that's when the debate began, and it became known as the information paradox. At first, two opposing schools of thought emerged. On one side, there were the relativists, around Hawking, Gibbons, and others, who argued that there was indeed an information trap, with some information irretrievably lost. On the other side were the quantum physicists, who insisted that something was wrong with that idea, that the paradox still hadn't been resolved.
Heated debates flared up around this question, similar to those that once surrounded the very existence of black holes themselves. On February 6, 1997, at the California Institute of Technology, three leading physicists decided to formally document their disagreement. On one side stood Stephen Hawking and Kip Thorne. Both were convinced that any information falling into a black hole is lost forever. Hawking's position was radical. He believed that the very process of evaporation destroys information. Thorne's view was more cautious. He assumed that information could not return to our universe but might slip away into another universe through the singularity inside a black hole. For us, however, it would still be lost. On the other side stood John Preskill, a quantum physics specialist from Caltech. Preskill was firmly convinced that the fundamental principles of quantum mechanics are inviolable. Information cannot simply vanish. It must somehow be preserved and eventually leak out of a black hole with its radiation. The text of the wager they signed stated, "When an initial pure quantum state undergoes gravitational collapse to form a black hole, the final state at the end of black hole evaporation will always be a pure quantum state." Put simply, they were arguing about what happens to information after the black hole evaporates, whether it disappears or remains in its entirety. In the words of a wager, in a pure quantum state. Hawking and Thorne bet on yes, that information is lost. Preskill bet on no. The stakes were symbolic, but with a sense of humor. The losing side would present the winner with an encyclopedia of their choice, from which information could be retrieved at will. It was a clever play on the ideas of losing and recovering information. But the origins of this scientific quarrel went back some 14 years earlier.
Werner Erhard, the founder of the widely publicized and controversial personal development movement EST, Erhard Seminars Training, used his considerable financial resources to bring together leading theoretical physicists, including Stephen Hawking, Richard Feynman, and Leonard Susskind, to discuss the most fundamental questions in physics. In 1983, Erhard once again gathered outstanding physicists at his mansion in San Francisco. Among those present were Stephen Hawking, Leonard Susskind, and Gerard T. Hooft. This was the core circle of physicists who focused their attention on Hawking's claim. The situation was surreal. Some of the greatest minds in the world were debating the fate of the universe and the laws of nature in an informal setting, inside the mansion of the founder of a popular self-improvement movement. It was at this meeting that Stephen Hawking, backed by mathematical derivation, fully formulated and presented his position that information inside black holes is irretrievably destroyed. Hawking was absolutely confident that he was right. He presented his calculations and, from his perspective, had mathematically demonstrated that information is lost. He left the gathering essentially declaring victory over one of the foundational principles of quantum mechanics. Leonard Susskind and Gerard T. Hooft were deeply troubled. Intuitively, and based on core principles of physics, they were convinced that Hawking was wrong, because the destruction of information would undermine the very foundation of quantum theory. However, they could not immediately identify the flaw in his complex reasoning. They left Erhard's mansion perplexed, but determined to prove that Hawking was mistaken. The meeting did not resolve the paradox. On the contrary, it thrust it before the physics community in its full severity. The participants had encountered a direct contradiction between two pillars of modern physics: general relativity as interpreted by Hawking, and the principles of quantum mechanics.
While the greatest minds of our time ponder the question whether or not information can exist forever, another, no less important question has remained behind the scene. How is information stored in the cosmos? If we can answer that, we will gain a better understanding of what happens to information near a black hole, and perhaps even uncover answers to questions we have not yet thought to ask.
In the December 7th, 2021 issue of the Astrophysical Journal Letters, an international team of researchers published unprecedentedly high-resolution radio images obtained in the microwave range. These images revealed in detail the structure of the jet emerging from the core of the elliptical galaxy M87, located about 55 million light-years from Earth. The length of this jet was found to be nearly 3,300 light-years. For comparison, the radius of the solar system is only about 0.002 light-years. What made this study of the M87 jet unique was that the researchers succeeded in mapping the three-dimensional structure of its magnetic field. It turned out that the jet's magnetic field forms a helical pattern strikingly reminiscent of the double helix of DNA. Astronomers believe that if such a phenomenon occurs in M87, then similar magnetic structures should exist in jets of other galaxies throughout the universe. Magnetic fields are capable of preserving information about past events, explosions, jet flows, mergers, as if recording a trace in time. It is even possible that such spiral structures play a role in transferring information to newly forming stars. At the end of the 1950s, radio astronomy was opening new horizons, driven by the rapid progress in signal detection and amplification technologies that had emerged during World War II. In 1959, the third Cambridge Catalogue of radio sources was published. One of the objects listed in this catalog posed a mystery worthy of Sherlock Holmes. This was 3C48, a source of unusually powerful radio emission whose spectrum did not match that of any known stars or galaxies. What was the nature of this object? This puzzle marked the beginning of one of the most significant astronomical discoveries of the 20th century. One of the leading researchers in this effort was Martin Ryle, an outstanding British physicist. His scientific career began in 1939. After graduating from Oxford, when he joined the Telecommunications Research Establishment, TRE, the main British center for radar and radio navigation research during and after World War II. During the war, Ryle worked in the Electronic Countermeasures Division. developing systems to interfere with German radar installations such as the Würzburg, used for directing anti-aircraft artillery. This experience later became foundational for his work in radio astronomy. After the war, in 1945, Ryle returned to the University of Cambridge and led a radio astronomy group at the Cavendish Laboratory, beginning a systematic hunt for cosmic radio sources. 10 years later, his group published the second Cambridge catalog, 2C, based on observations at 81.5 megahertz using a radio interferometer. However, the catalog had significant drawbacks. The low frequency of the receiver limited the resolution, due to which closely located sources overlapped each other, creating false trails, significantly reducing the accuracy and value of the catalog for science. To overcome this, Ryle's team decided to produce a new catalog at a higher frequency, 159 megahertz. Ryle's radio interferometer worked like cross-examining multiple witnesses. It combined signals from several antennas placed far apart. By measuring the phase differences between the signals received by each antenna, the instrument could determine the angular position of a radio source and filter out noise. The interferometer provided significantly higher resolution than any single radio telescope. At the same time, the use of an interferometer was partly a strategic necessity. Ryle knew that research groups, especially in the United States, had far better funding. He cultivated a culture of the Cambridge Fortress, keeping his methods secret to avoid being overtaken. His wartime experience had taught him to value clever electronic techniques over brute force solutions. The result of this work was the creation of an improved phase-switching interferometer. This approach allowed the use of high-gain preamplifiers directly at the antennas, greatly reducing noise and dramatically improving positional accuracy. This technique soon became worldwide standard for radio interferometers. The third Cambridge catalog, published in 1959, included 471 radio sources. Among them stood the enigmatic 3C48. A turning point in the investigation of the case of 3C48 came through another suspect, 3C273, the brightest source in the catalog. If astronomers could match radio coordinates with an optical image in a telescope, they would have a far better chance of understanding the nature of these unusual objects. This connection was made in 1962, when astronomer Cyril Hazard, using the Parkes Radio Telescope in New South Wales, Australia, observed the occultation of 3C273 by the Moon, allowing him to determine its position precisely. These data enabled Alan Sandage, renowned for his work in galaxy classification and cosmology, to identify 3C273 in visible light as a star-like object of 13th magnitude. 1 year later, American astronomer Martin Schmidt performed a spectral analysis of 3C273. He found a redshift of Z equals 0.158, meaning that 3C273 is located about 2 billion light-years away. No star could emit that much energy. It became clear that 3C273 is a very distant galaxy, appearing star-like only because of its extreme distance. Thus, quasars, quasi-stellar objects, were discovered. This breakthrough provided the key to solving the mystery of 3C48. Alan Sandage and Thomas Matthews identified 3C48 optically. Its spectrum was as unusual as that of 3C273. Further analysis showed a redshift of Z equals 0.367, placing 3C48 even farther away, yet emitting enormous amounts of energy toward us. And so, the first quasars appeared on astronomical maps.
The nature of these objects remained one of the greatest mysteries of the universe. Their incredible luminosity, sometimes outshining hundreds of galaxies, and their compact size, as evidenced by rapid fluctuations in brightness, defined all existing physical models. It became evident that classical mechanisms, such as nuclear fusion or the gravitational collapse of ordinary stars, could not possibly produce such immense power. Among the hypotheses proposed to explain the nature of quasars were the explosions of numerous supernovae, the existence of gigantic stars, or even white holes, the hypothetical counterparts to the black holes. The key events that resolved these debates took place in 1969.
On August 16, 1969, in volume 223 of the journal Nature, British astrophysicist Donald Lynden-Bell presented a hypothesis. In his analysis, Lynden-Bell demonstrated that the source of the enormous energy output of quasars is supermassive black holes located at the centers of galaxies. This model explained the high luminosity of quasars as the result of gravitational energy released by the infall of gas and dust into a black hole. Such a process can convert between 6% and 30% of the mass of infalling matter into energy, far surpassing the efficiency of nuclear fusion. The theoretical foundation of this hypothesis had been laid earlier in the work of Soviet physicist Yakov Zeldovich and American astrophysicist Edwin Ernest Salpeter. The scientific community initially responded to this idea with skepticism. The main reason was that the very concept of black holes at the time was considered purely theoretical. There was still no direct observational evidence for their existence, and many scientists approached the idea with caution and doubt.
So, in the 70s and 80s, people realized there were energetic, violent phenomena happening in the center of galaxies, some galaxies, not all. And over time, it was clear that the only explanation is a supermassive black hole accreting material and basically generating enormous amounts of energy. So that was a big draw. Once you've decided that every galaxy has a black hole, which is pretty much what we've decided, they may be hard to find, but if you look hard enough, you do find them. The question then becomes, why are most of them dark most of the time? So why, if black holes can occasionally erupt into activity, and then we call them quasars basically, where the central object outshines the entire rest of the galaxy by a factor of hundreds or thousands, that's incredible.
But quasars turned out to be not only the most powerful sources of radiation in the universe, they also presented scientists with another mystery. The oldest quasar known today is UHZ-1, discovered in 2023. According to a study published in Nature Astronomy, UHZ-1 has a redshift of Z equals 10.1, which means that the light from this quasar has traveled 13.72 billion years to reach Earth. Meanwhile, the age of the universe is estimated to be 13.8 billion years. This implies that UHZ-1 appeared almost immediately after the Big Bang. Scientists are now confronted with a fundamental question: how could supermassive black holes have formed so quickly? Current cosmological models fail to explain how these objects could have grown so rapidly and accumulated matter on this scale.
As people studied high redshift galaxies, they found unusually big, uncomfortably big black holes in very high redshift galaxies. So if you find a billion solar mass black hole in a galaxy that's only a billion years after the Big Bang, that's hard to do. Growing a black hole that big, that fast is challenging theoretically and with simulations. I think there's a lot of activity and interest in the sort of chicken and egg question, because if every galaxy has a black hole, which came first? Did the black hole come first or the galaxy come first? We have a theory of cosmology, generally supported by a lot of data, that galaxies grow in a hierarchical way, that the early universe, which was hotter and denser, formed small dwarf galaxies first, and then by gravity they aggregated together and merged into bigger galaxies. And we know galaxies are formed by mergers and by infall. We can see it even happening now in the Milky Way. So that's a story that we believe. And then the question is, how does the black hole that's at the center of every galaxy fit into this story?
Having identified that the energy source of quasars is black holes, science has in turn given rise to another mystery. According to current data, the mass of quasars ranges from millions to billions of solar masses. But there's yet another mystery surrounding supermassive black holes believed to reside at the center of galaxies, and their masses are also in the millions to billions of solar masses. Existing theories propose that black holes form from collapsing stars. The most massive star known to us, R136A1, has a mass of about 200 solar masses. If it were to collapse into a black hole, its mass would be no more than approximately 150 solar masses. Compared to what we observe in galactic centers, that would make it a mere microbe, a speck of dust. Yet somehow, this tiny black hole would have to grow from 150 solar masses to 1 million, or even 10 billion. The problem is, we don't observe any of the in-between stages. Just like in biology, where we don't find transitional species that should be preserved in Earth's geological layers. All known animal and planet species appear before us in fully formed states. Similarly, in space, we observe stellar mass black holes and supermassive giants in the centers of the galaxies, but no in-between stages. In modern astrophysics, it is known as intermediate black hole problem. And this raises a question. Could the central structure of galaxies have some additional functional role beyond fueling quasar outbursts? We'll return to this with a remarkable analogy we uncovered while preparing this film. And we'd like to share it with you today. But before that, let's rise about the scale of galaxies. According to modern astronomy, galaxies do not exist in isolation in space. They are gathered into clusters. And the most interesting thing about these clusters is not the galaxies themselves, but what lies between them.
Galaxy clusters contain extremely hot gas. It's a diffuse gas that we can observe in X-rays because it is so hot that it naturally emits at these wavelengths. So we can observe them using satellites in space. Meanwhile, the cold flows in this concept correspond to these filamentary structures, which are not only cold, but can also be observed in warm gas. So they're multiphase. And this cold gas can have a temperature of less than 100 Kelvin. As I was telling you, galactic jets interact with the gas, and as this gas interacts with the jets, and the jets with the surrounding gas, they create these filaments, and those filaments go on to form stars. Well, first of all, the gas isn't molecular yet. It's going to collapse and form stars, and those stars will become part of the galaxy. So yes, this process affects star formation, and also the stellar population that makes up galaxies. Therefore, it plays a very important role in determining the properties of galaxies.
Galaxy clusters are the largest known structures in the universe. Some of them contain thousands of galaxies. As we have already learned, the space between galaxies is not actually empty. It is a kind of nourishing medium in which these islands of stars float. Scientists have established that the mass of this gaseous medium, the intracluster medium, ICM, actually exceeds the total mass of the galaxies themselves. The intracluster medium is a vast volume of extremely rarefied yet incredibly hot plasma that fills the space between galaxies within a cluster. At first glance, it may seem like just gas, but it is something far more complex and mysterious. Its high temperature, from 10 to 100 million degrees Celsius, makes the intracluster medium a source of X-ray radiation. And it is primarily through this X-ray emission that we are able to observe it. Valeria Olivares, an astrophysicist and assistant professor at the University of Santiago, coordinated a team of researchers observing 7 galaxy clusters using the Chandra X-ray Observatory and the VLT optical telescope in Chile. The scientists obtained evidence of a paradoxical phenomenon. Jets ejected from the centers of galaxies can cool the very gas that is necessary for their own fueling and further growth.
At the center of these clusters is a special galaxy known as the brightest cluster galaxy. It is the most luminous, massive, and active galaxy, and it hosts a supermassive black hole in an active state. So, it is capable of creating a feedback loop by producing jets. These jets create the bubbles you mentioned, which then interact with the surrounding gas known as the intracluster medium. It's a very hot gas, with temperatures reaching up to 10 million degrees Celsius. Basically, we believe that magnetic fields help maintain the elongated, filamentary structure of these filaments. More importantly, they prevent these filaments, which contain very dense and very cold molecular clouds, from collapsing and forming a large number of stars. So they help to prevent excessive star formation.
Molecular interstellar clouds are vast, cold, and dense regions composed primarily of molecular hydrogen. These enormous cosmic structures are the very cradles of star formation, the main engines driving stellar birth across the universe. This raises a question: how is it possible that magnetic fields within molecular clouds prevent star formation? It's a paradox, because according to modern science, the primary role of these clouds is to form stars. But if somehow the environment within them is being deliberately maintained in a state that artificially suppresses star formation, perhaps this phenomenon has a meaning. While working on this film, we stumbled upon a fascinating analogy. Incredibly, the role of the intracluster medium turned out to closely resemble the role of the extracellular matrix in the human body. It's truly remarkable how similar these phenomena are.
Modern theories of galaxy formation involving supermassive black holes, together with the informational holographic principle, allow for the possibility that the central object of a galaxy, traditionally considered a supermassive black hole, may actually perform entirely different functions. Let us suppose that these extensive regions at the centers of galaxies are zones of concentration of an informational field that governs the dynamics and evolution of galaxies. Within the framework of this hypothesis, the foundation of any galaxy is an informational field in which the galaxy already exists in its fully formed state, and its material manifestation is only a matter of time. The informational field resembles the phantom image observed in Kirlian photography, where the outline of a leaf remains visible even after part of it has been cut away. In the same way, a salamander can regenerate its tail, and cellular tissues can regenerate in any living organism. However, salamanders possess unique biological conditions that allow this regeneration. These conditions arise because the wound surface in salamanders releases a special substance analogous to the extracellular matrix. It is the presence of this matrix that attracts stem cells to the injury site. But how do stem cells know what to become? Muscle, blood vessel, or something else? Research has shown that the specialization of stem cells within the extracellular matrix depends on the matrix's density, which in turn is influenced by the informational phantom. Thus, the matrix acts as a mediator between informational structures and material structures. According to this hypothesis, similar processes occur in the formation of galaxies. The informational field already contains a blueprint of what the galaxy will become. In this cosmic analogy, the interstellar medium corresponds to the extracellular matrix, and the intracluster medium plays the role of stem cells, from which stars, planets, and other structures form according to the given informational matrix. The extracellular matrix allows cells to migrate within it, provides structural connections between them through fibers in the basal membrane, participates in tissue formation, gives tissue strength, maintains the shape of cells and organs, and performs signaling, filtering, and other complex functions. In living organisms, it performs the same role that interstellar matter performs in space. Moreover, if we examine the structure of the human spine, we can see a direct analogy between certain galaxies and the intervertebral disc. The disc, in its shape and mysterious origins, resembles a lenticular galaxy, which also takes the form of a biconvex lens. Such a comparison may lead to profound implications, for the forces that shaped lenticular galaxies are as mysterious and poorly understood as the forces that gave rise to living organisms. In embryology, there is the concept of mesenchyme, an embryonic tissue composed of loosely arranged cells immersed in a network of proteins and fluid known as the extracellular matrix. Mesenchyme gives rise to most of the body's connective tissues: skeleton, bone and cartilage, blood, and the structures of the vascular and lymphatic systems. Mesenchyme is characterized by low structural organization. It contains a gel-like matrix rich in hyaluronic acid, less organized than in mature tissues. It is highly plastic, but it requires signals from neighboring tissues in order to develop structure. Here we find a striking analogy with protostellar clouds, which require external triggers, shock waves, magnetic fields, or turbulence, to condense into stars. The development of mesenchymal cells is guided by a program encoded in the embryo's DNA. Likewise, in space, where the function of DNA can be performed by spiral magnetic fields found in a jet ejected from the core of the galaxy M87, And here is what is most intriguing. Fragments of the notochord, the precursor of the vertebral column, persist only in the gel-like nucleus pulposus of the intervertebral discs. Perhaps, by analogy, the centers of galaxies do not contain black holes at all, but rather a kind of primordial informational program that binds together the entire fabric of the universe.
Now that we have a better understanding of the role information plays in the process of star formation, it's time to return to our central question. What happens to information near a black hole? In quantum mechanics, there is a rule that can be compared to a perfect library catalog, unitarity. This catalog guarantees that every book, that is, information about a quantum state, can always be traced and recovered, even if the library catches fire and it burns to the ground. The loss of information would mean that someone burned the books with no possibility of restoring their contents. Picture this. You write a letter, and then you burn it. In everyday terms, the ashes certainly won't reveal what was written in the letter. In other words, the information it contained seems lost forever. In quantum physics, the ashes must retain information about the letter, encoded with them in such a way that the original message can, in principle, be reconstructed if you know how. The loss of information in a black hole would be analogous to the ashes containing no trace of the letter whatsoever. What would that mean? A system where information exists today but vanishes tomorrow becomes completely unpredictable. And here's the critical reason why information cannot simply disappear. If the symmetry of time is broken, then the law of conservation of energy is no longer guaranteed to hold. In other words, if the universe can forget information, then it might just as easily forget how much energy it had. Such cosmic forgetfulness would allow energy to vanish into nothing or appear out of nowhere. That is why physicists defend the principle of information conservation so fiercely, because abandoning it would tear apart the very foundations of science, and with them, our ability to understand and model the universe through the laws of physics.
We were very suspicious of Stephen's claim, but for a while we weren't sure why. What's so bad about losing a bit of information inside a black hole? Then it dawned on us, losing information is the same as generating entropy, and generating entropy means generating heat. Together with another colleague, Michael Peskin, we made an estimate based on Stephen's theory. We found that if Stephen was right, empty space would heat up to 1,000 billion degrees in a tiny fraction of a second.
To continue our investigation into what happens to information near a black hole, we need to introduce one more concept: entropy. In simple terms, entropy is a measure of disorder. The more order in a system, the lower its entropy. Another analogy of entropy is the number of options. Imagine your room in two different states, perfectly tidy or completely messy. There are only a few ways things can be arranged for a room to look neat. That's low entropy. In a state of disorder, the same objects can be scattered in millions of different ways. That's high entropy. And that's the point. The more possible configurations of disorder, the higher the entropy. In the case of a black hole, entropy reflects the amount of information associated with its state.
So, what is entropy? It's a measure of disorder. In other words, it's a measure of the information we've lost about a system. The second law of thermodynamics tells us that in an isolated system, unlike, for example, a living system that constantly interacts with its environment, entropy increases over time. In other words, the system's usable energy decreases, and we're left with less and less information about it.
In the early 1970s, the physics of black holes was undergoing a period of rapid development. One of the turning points in this development occurred in 1972, when Jacob Bekenstein defended his doctoral dissertation at Princeton University on the topic of black hole entropy. Bekenstein was a graduate student of John Wheeler, the very physicist who had introduced the term black hole into scientific usage. Wheeler was skeptical about his student's research topic because the concept of entropy implied that black holes could have temperature and possibly radiate, which at the time seemed absurd. Nevertheless, Bekenstein insisted on his hypothesis. He developed this idea in detail and presented it in his paper, Black Holes and Entropy, published in the journal Physical Review in 1973. In that work, he proposed for the first time that the entropy of a black hole is proportional to the area of its event horizon. Why surface area rather than the volume? In ordinary physical systems, entropy is always proportional to volume. The more space available, the more disorder the system can contain, just as the number of gas molecules in a room, where you have just cleaned up, is directly proportional to the room's volume. The larger the space, the more air it holds. However, for a black hole, the volume inside the event horizon has no physical meaning, because space-time in that region is inaccessible to observation. Therefore, the only physically meaningful measure remaining is the surface. Bekenstein's idea that all information about the contents of a black hole is encoded on its surface laid the foundation for the holographic principle and radically changed understanding of black holes, linking them to thermodynamics and quantum information theory. Thus, the question of information preservation became central.
It seems we're getting closer to answering the mystery of our Bagel hole. And surprisingly, the answer may lie right on the surface of the black hole itself. More precisely, on the part depicted by the physicist Jean-Pierre Luminet in his famous computer rendering back in 1978. So, what do we actually know about it today?
What we're seeing is not, in fact, the full accretion disk as I calculated it back in 1978. Rather, it's a finer and somewhat mysterious structure known as the photon ring. The photon ring is essentially a sequence, a cluster of secondary, tertiary, and even higher order images.
The photon ring is an extremely thin and bright structure, located at the very edge of a black hole's shadow. It is composed of photons that have been captured by the black hole. Under the influence of its immense gravitational forces, these photons orbit the black hole one or several times before escaping its pull and reaching us. In May 2022, a team of scientists, Shahar Hadar, Daniel Kapes, Alexandru Lupsaska, and Andrew Strominger, studied the photon ring of the M87 black hole. They discovered that the photon ring is not merely an optical effect, but a source of information about the black hole's internal structure. This information is encoded in the properties and trajectories of the photons. In fact, the photon ring of the black hole, M87, is a hologram that contains all the information about its inner structure. Since the light forming the ring travels close to the event horizon, where that information is encoded. Thus, the study provided experimental support for the ideas of black hole entropy, first introduced in Jacob Bekenstein's dissertation, and later developed into the holographic principle by Gerard de Hooft. This principle asserts that all the information contained within a three-dimensional volume of a black hole can be encoded on its two-dimensional event horizon surface. Leonard Susskind further expanded upon these ideas in his article, The World as a Hologram. Here then is the conclusion that Hooft and I had reached. The three-dimensional world of ordinary experience is the universe filled with galaxies, stars, planets, houses, boulders, and people. Is a hologram, an image of reality coded on a distant two-dimensional surface. This new law of physics, known as the holographic principle, asserts that everything inside a region of space can be described by bits of information restricted to the boundary.
So, what have we learned? Most likely, if a passing baker were to drop a bagel into a black hole, all the information about it would end up on the surface of the black hole as a two-dimensional hologram smeared across its entire surface. What happens to the actual matter of the bagel? Where does it go? What about its mass?
Let's take a closer look. Democritus says that when atoms come together, what matters is their shape, their configuration within a structure, and how they combine. He illustrates this with the example of the letters of the alphabet. There is something in this idea that goes beyond the atoms themselves. What truly matters is the way they combine with one another. On May 14, 1907, in the journal Annalen der Physik, in an article titled On the Inertia of Energy Required by the Relativity Principle, Albert Einstein published his most famous equation in the form we know today, E equals mc squared. From this equation, it followed that mass and energy are equivalent. This simple formula showed that mass can vanish when energy is released. 22 years later, in 1927, Nobel laureate Francis Aston introduced a new concept in physics, the mass defect. The essence of the mass defect is that the mass of a body does not depend on the number of its constituent particles, but rather on how these particles are bound together. In other words, the mass of an object resides in the bonds between the particles that make it up. When these bonds are broken, the energy that once held them together is released. The residents of Hiroshima and Nagasaki experienced firsthand what the mass defect means in practice. One can only hope that such a tragedy will never happen again, and that all scientific discoveries will serve solely for the benefit of humankind. But let's return to the microscopic world. Take, for example, the proton. It consists of 3 quarks. However, if we add up the masses of these quarks, we obtain only about 1% of the proton's actual mass. So where do the remaining 99% come from? This mass arises from the binding energy, according to the relation m equals E divided by c squared. In other words, 99% of the proton's mass is the energy of the strong interaction that holds the quarks together inside the proton. But what creates the remaining 1% of the proton's mass? To solve this puzzle and describe all types of particle interactions, in the 1950s to 1960s, physicists attempted to develop a unified field theory. This theory was expected to explain the origin of quark masses and to describe all kinds of interactions between particles. The work began with the unification of electromagnetic and weak interactions into a single framework, the electro-weak interaction. However, the electroweak theory worked perfectly only if the particles involved were massless. So what about mass? Soon, a solution was found. On October 19, 1964, the journal Physical Review Letters published an article titled Broken Symmetries and the Masses of Gauge Bosons. It was an article by Peter Higgs, in which he described a certain hypothetical field. The uniqueness of this field was that elementary particles acquire mass through their interaction with it. This hypothesis was a breakthrough in understanding the nature of mass. But like any hypothesis, it still required experimental confirmation.
Imagine placing a pencil perfectly upright on its tip, balanced on a flat surface. There is no definite side. The pencil can fall in any direction. It's a state of symmetry. But the moment you let go, it falls one way or another. This is the analogy physicists use to describe what is thought to have happened in the early universe. In the beginning, all particles were massless. The Higgs field was in its symmetric state with an average value of 0. At that time, the electromagnetic and weak forces were unified into a single electroweak interaction. As the universe cooled, it began to fall into a more stable, lower energy state. For the Higgs field, the lowest energy state turned out to be one where its value is not 0, but approximately 246 giga-electron-volts. The field had to choose this specific non-zero value from an infinite number of equally possible options, just as the pencil has to choose a single direction in which to fall. This phenomenon became known as spontaneous symmetry breaking. For the next 50 years, theoretical physics built its understanding of particle mass around the concept of the Higgs field. However, for a long time, this remained purely a mathematical concept. To test the theory in practice, scientists needed tools powerful enough to recreate the extreme conditions under which the hypothetical Higgs boson could reveal itself. It was this boson that was expected to confirm or disprove the existence of the field that is believed to give mass to elementary particles.
In March 1984, a conference was held in Switzerland dedicated to the Large Hadron Collider. At that conference, a decision was made to build a particle accelerator capable of reaching the energies at which scientists expected the Higgs boson to appear. Construction of the collider began in 2001 and posed enormous engineering challenges. A key stage was the creation of a cryogenic line to cool thousands of the accelerator's superconducting magnets to a temperature of minus 271.3 degrees Celsius, minus 456.3 degrees Fahrenheit. This work took 5 years to complete. The last superconducting magnet was installed in April 2007, and another year was needed to connect all the equipment. Finally, on September 10, 2008, the first proton beam was launched toward its target. The search for the Higgs boson had begun. However, just 9 days after the collider started operating, a serious accident occurred, one that almost put an end to the possibility of detecting the elusive boson. A faulty electrical connection between two magnets melted, triggering a powerful electrical arc that ruptured the cooling system. As a result, about 6 metric tons, 6.6 US tons, of liquid helium were released into the accelerator tunnel. Fortunately, the situation was brought under control. Repairs and the implementation of improved safety systems took more than a year. This incident underscored the complexity and risks associated with operating such a massive scientific installation. By the time full-scale experiments began in 2010, the proton beam energy in the Large Hadron Collider had reached 3.5 tera-electron-volts, TeV, about 3.6 times higher than that of the Tevatron, the most powerful hadron collider at the time. Research continued. And then, on July 4, 2012, a historic seminar took place at the European Organization for Nuclear Research, CERN. 2 independent research teams, working with the ATLAS and CMS detectors of the Large Hadron Collider, presented their results. Both groups announced the discovery of a new particle whose properties matched those predicted for the Higgs boson, first theorized by Peter Higgs 48 years earlier. The discovery suggested with a certain degree of probability that the Higgs field, which endows particles with mass, does exist.
What did CERN physicists actually see? According to modern science, every elementary particle corresponds to its own field. The particles are local excitations of those fields, or as physicists say, resonances. For example, A photon corresponds to the electromagnetic field. An electron corresponds to the electron field, known in physics as fermionic or spinor field. Likewise, the Higgs field should have its own associated particle, its own resonance. The paradox of what happened on July 4th, 2012, when the discovery of the Higgs boson was officially announced, is this. Physicists did not actually observe the boson itself as a distinct particle of the excited field. What was actually detected was a surge of energy, one that matched the theoretical predictions. While studying the data from the Large Hadron Collider, a particular fact caught our attention. To detect a single Higgs boson, approximately 10 billion collisions are required. That seems strange. According to theory, the Higgs field permeates all of space in the universe. So how is it possible that detecting this boson requires 10 billion collisions? 10 billion! This was not the last question raised by the phenomenon known as the Higgs boson. Here's something else that caught our attention. The phenomenon only appears under very specific conditions. It isn't detected directly, only through its decay products. Its lifetime is extremely short, about 10 to the power of minus 22 seconds. We analyzed each of these points carefully to gain a deeper understanding of what was actually discovered in the collider. Here are our conclusions. The phenomenon appears only under certain conditions. This suggests we are dealing with a localized state of the field, one that doesn't exist continuously. If the Higgs field is truly present everywhere, then the Higgs boson should be detected in every experiment. But the Large Hadron Collider detects it only once every 10 billion collisions. The phenomenon is not observed directly, but only through its decay products. What we see is not the object itself or its direct interaction, like with photons or electrons, but rather its trace, its imprint. It's like finding a pile of tiny ceramic shreds on the floor. All you can tell by looking at the pieces is that the object was made of ceramic, but you can't say for sure whether it was a plate, a cup, or a vase. Likewise, decay products alone can't definitely tell us what they originally formed when they were still together. This makes it one of the shortest lived entities known to science. Only the W and Z bosons, carriers of the weak nuclear force, and the top quark with lifetimes around 10 to the power of minus 25 seconds live even less. But the W and Z bosons have clear and well-defined decay channels. In the Higgs boson, decays are rare and diverse, and they occur at the background level, which makes it very difficult to detect. Taken together, these facts point to one conclusion. The Higgs boson is not exactly a particle in the usual sense. So what is it really? We didn't bring up the story of the Large Hadron Collider by chance. It was there that something was discovered which might hold the key to our question about the Bagel and its hole falling into a black hole. Today, we know that particles don't actually possess mass on their own. Their mass is given to them by the Higgs field. But what about black holes themselves? What gives them their mass? Traditionally, the mass of a black hole is determined by observing the orbits of nearby stars, which trajectories are reflected in its gravitational field, by gravitational lenses and by gravitational waves. In all these cases, we see the effect of mass, but we don't actually know what carries this mass. But what if the mass of a black hole is fictitious? Every modern theory describing black holes is built on the assumption that they do have mass. This assumption isn't questioned, since the gravitational field of a black hole clearly influences nearby objects. It's precisely this interaction that eventually convinced science that black holes must exist. But what if things aren't as we think? In trying to unravel the mysteries hidden within black holes, we came across a theory that offers a radical explanation for their mass, one that is based on a discovery made with the help of the Large Hadron Collider roughly 10 years ago.
We have not, of course, observed black holes directly, but we have seen extremely energetic phenomena in distant galaxies, so intense that they can only be explained by the release of gravitational energy from black holes. From this, we've been able to estimate their mass.
According to the modern understanding of quantum physics, no elementary particle possesses mass by itself. Mass is considered not as an innate property, but as a result of interaction with a fundamental field, the Higgs field. This field permeates all space throughout the universe. When an elementary particle moves through it, it is as if it encounters a viscous medium. Depending on how strongly a particle feels the Higgs field, it acquires a greater or lesser mass. For example, the electron interacts with the field moderately, which is why it is light, whereas the W boson interacts much more strongly, and therefore is heavier. The Higgs field does not create gravity, it merely endows particles with mass. Gravity is a consequence of the presence of mass and energy. According to Einstein's general theory of relativity, mass-energy curves space-time, and this curvature is what we perceive as gravitational attraction. However, for a particle to engage in gravitational interaction, it must first acquire mass through its interaction with the Higgs field. For example, if we place an apple on a tightly stretched sheet, the sheet will sag, forming a depression around the apple. This simple analogy vividly illustrates how the general theory of relativity describes the distortion of space caused by objects that have mass. Now let us turn to an entirely new hypothesis proposed in 2025 in the paper, Grid Higgs Framework, an entropic and structural theory of gravity, dark matter, and black holes. The authors of this work suggest that black holes are reinterpreted as collapse regions where the grid structure fails under extreme entropy gradients. In other words, they propose that a black hole is quite literally a hole, a rupture in the Higgs field. In this case, the interior of a black hole would represent absolute void, since within the region where the Higgs field is ruptured, no mass can exist. There are no particles capable of generating it. Consequently, at the boundary of the Higgs field rupture, that is, at the event horizon of the black hole, matter must undergo complete disintegration. This occurs because the Higgs field acts as the binding medium of matter. If the field ceases to exist in a given region, matter can no longer retain its familiar properties there. This approach, however, leaves an open question. If a black hole has no mass, why is it able to attract material objects and alter their trajectories? As we have just seen, mass is the source of gravity. The greater the mass of an object, the more it curves space-time and attracts other bodies. But objects acquire mass through their interaction with the Higgs field. According to the assumptions made in Grid Higgs Framework, an entropic and structural theory of gravity, dark matter, and black holes, if a black hole is not a massive object, but rather a rupture in the Higgs field, then it does not need to possess mass in order to curve space-time. Thus, the concept of massless gravity becomes possible, a scenario in which the geometry of space-time can be distorted even in the absence of mass within that region. In his paper, The Vacuum Theory of Matter Annihilation, Jakaya wrote, "Our starting point is the statement of Zeldovich and Novikov. A singularity exists even where there is no matter. From this, it necessarily follows that inside a black hole, beyond the Schwarzschild radius, there is no material mass with the notorious infinite density confined within a zero volume. Instead, there exists only a localized compression of the vacuum, manifesting as a gravitational field of extreme intensity. In other words, when the radius becomes smaller than the gravitational radius, the property of curvature transforms into twist. And that is what constitutes a black hole. Space can be divided into tiny Planck-scale cells, resembling a three-dimensional chessboard. Each cell can store a single bit of information. A bit can be represented as a very simple particle. Each cell either contains a particle or it does not. One can also imagine these cells as a giant playing field for a game of tic-tac-toe.
So, now we know almost everything about the adventures of our Bagel near a black hole. What remains is to figure out what happens to space itself. According to Einstein's general theory of relativity, space-time curves under the influence of mass and energy. This curvature is what we perceive as gravity. Near massive objects, such as stars and planets, this field compels objects to move along curved trajectories. In the case of black holes, Einstein's theory predicts the existence of a singularity, a region at the very center where the curvature of space-time becomes infinite. Beyond the event horizon, the very notion of outside simply ceases to exist. But what is space in and of itself? Can it collapse entirely, reaching infinite curvature as general relativity suggests? Or could it rupture, much like we just saw with the Higgs field when symmetry is broken?
The idea behind loop quantum gravity is to discretize space and time entirely. In other words, if you want to quantize gravity, that is to make it discrete, then since in general relativity gravity is geometry, what you're essentially doing is quantizing geometry. So instead of working with continuous spacetime, as is still done in string theory for example, where you even have to add extra spatial dimensions, in loop quantum gravity we continue to work with three-dimensional space and time, but instead of being continuous, space-time is discretized.
In general relativity, any point in space can be divided infinitely. In loop quantum gravity, space has a limit. This limit is a set of discretes, or pixels, similar to the pixels of an image on your computer or phone screen. The existence of spatial discreteness explains the absence of singularities, replacing them with a maximum curvature defined by the size of the spatial pixels. These pixels of space are on the order of the Planck length. Beyond this scale, matter as such ceases to exist. Quantum gravity is called loop because its fundamental building blocks are one-dimensional lines, loops. From these loops, like threads, the fabric of the entire space of the universe is woven. A loop is not a physical object but an abstract excitation line of the gravitational field, a quantum of space itself. An elementary loop represents an elementary portion of area, approximately equal to the Planck area, on the order of 10 to the minus 70 square meters. The interactions of such loops form a spin network. The nodes where the loop lines intersect correspond to quanta of volume. Together, the loops and the nodes create a discrete, pixelated structure of space. Thus, in loop quantum gravity, space is not an empty stage, but a dynamic network of interconnected loops.
So there is the equivalent of elementary grains of space and possibly also of elementary grains of time, the equivalent of atoms of space and atoms of time. In this kind of framework, singularities are already eliminated because, for example, during gravitational collapse, there comes a point where we hit the elementary grain of space, which is not infinitely small.
Let's take a step back and recap what we've discovered so far. We now know that the entire universe is filled with Planck-scale cells, like the pixels on the screen you're watching this film on. We also know that a black hole is a truly unique object in our universe. Above all, it creates immense gravity. Yet, paradoxically, it has no mass of its own. It is believed that there is nothing inside a black hole, that everything takes place on its surface. The final step is to understand what happens to the matter that carries the information, and at last to solve the riddle of the Bagel's hole. This question is the central problem of modern physics. Hawking radiation, which causes black holes to evaporate, seems to be completely random and carries no information about what has fallen in. When a black hole disappears, the information about the swallowed matter would be lost forever. And that directly contradicts the laws of quantum mechanics. even though Stephen Hawking himself once defended this paradox. So, how can this contradiction be resolved?
To address the problem of information preservation in a black hole, in 2012 a group of physicists, Ahmed Almheri, Donald Merolf, Joseph Polchinski, and James Sully, this group is often referred to by the first letters of their surnames, AMPS, proposed the so-called firewall hypothesis. The scientists suggested a radical solution to the informational paradox, sacrificing one of the principles of quantum mechanics. The principle regarded as the least sacred cow to be set aside in favor of common sense was the principle of equivalence. The AMPS hypothesis states, instead of a smooth event horizon as predicted by general relativity, there exists a high-energy zone at the boundary of a black hole where quantum mechanics dominates, creating a barrier that destroys or transforms any matter falling onto it. In other words, any matter that reaches this horizon does not pass through it smoothly, as Einstein assumed, but instead instantly incinerates in this wall, turning into energy. Under such an approach, it can be assumed that the information associated with this matter may potentially be encoded in Hawking radiation, rather than disappearing. If this hypothesis is correct, then the role of black holes in the universe becomes clear. On July 21, 2004 in Dublin, Ireland, the 17th International Conference on General Relativity and Gravitation took place. This is one of the most prestigious and significant events for theoretical physicists, cosmologists, and astrophysicists from around the world. Stephen Hawking's presence had always been a central attraction at such conferences, but this time expectations were especially high. A few days before his report, rumors began to circulate that he was preparing to make a sensational announcement and reconsider his views on one of the fundamental problems he had worked on for decades. During his presentation, Stephen Hawking introduced a new, and at that time, revolutionary theory. He stated that black holes are not absolute prisons for information, as he had previously claimed. Here is what he said. Information is not destroyed. In contrast to his earlier position, Hawking now asserted that information absorbed by a black hole does not disappear without a trace. Distortion, rather than destruction. A black hole greatly distorts information, but ultimately, in the process of its evaporation through Hawking radiation, this information eventually returns to the universe, although in a strongly altered form. He then stated,
I'm sorry to disappoint science fiction fans, but if information is preserved, there is no possibility of using black holes to travel to other universes.
Thus, the idea of wormholes between worlds inside black holes was effectively settled. The climax of the presentation was Hawking's public acknowledgement that his opponent in the debate, John Preskill, was right. This was a dramatic and very human moment for the scientific community. Hawking publicly admitted his mistake. To settle his wager, Hawking presented Preskill with the baseball encyclopedia, Total Baseball, the ultimate baseball encyclopedia. This voluminous 2,301-page reference work is considered an authoritative source on baseball statistics and history. The choice was both deliberate and symbolic. An encyclopedia is a source from which, as Hawking noted, information can be easily retrieved at any time, in contrast to information that has passed through a black hole.
Even if there is a single possible unified theory, it is just a set of rules and equations. What is it that breathes fire into these equations and creates the universe they describe?
So, now it's time to return to the questions we posed at the very beginning of this film. What are black holes and why does the universe need them? As we've learned, a stellar black hole is not really a cosmic object in the usual sense. A black hole is a special region of space where matter is disposed of. Just as an eraser wipes writing off a sheet of paper, A black hole wipes space clean of excess matter. The matter disappears completely, never actually entering the hole itself. In this way, black holes serve as cosmic cleaners, destroying matter and stripping it of the information it carries. But this applies only to stellar black holes. At the centers of galaxies, as we've seen, entirely different processes unfold. And what about our Bagel? Every material thing is made of atoms. But atoms by themselves don't create form. It's the relationships between them, the information encoded in their bonds, that shapes them into structures. That information is what gathers atoms into a bagel with a hole. When the bagel approaches a black hole, those bonds completely unravel. Information is torn away from them. At that moment, both the form and the hole, which was part of the structure, vanish. All that remains are fragments of matter, clusters stripped of any program for existence, much like the Higgs boson glimpsed in the collider. Since the information that once held these fragments together as a whole is now separated from them, their lifetime is extremely short, comparable to the fleeting existence of the Higgs boson itself. This is true for any substance that drifts near a black hole. Once its informational foundation is lost, the elementary particles that once made up the bagel no longer hold together. To an outside observer, the matter disappears completely, where just a moment ago there was a bagel drifting from a rocket. All that remains are short-lived, outbound clusters, and shortly after, nothing but an empty space-time scaffold, stretching across the entire universe. That's it. Our investigation comes to an end, and the most important point we'd like to leave you with is this: to ensure that such a region of space, the very kind we've just explored, never appears near our own sun, humanity must prove it deserves to continue living. Today, we face challenges that could destroy the biosphere of this planet within the next decade. The most urgent of these are climate change and microplastics. The renowned British experimental physicist Brian Cox, who worked on the Large Hadron Collider, made his statement in his address to the COP26 Climate Summit. It's possible that there is only one civilization in the Milky Way galaxy. There may only have been one, and there may only ever be one. And that's us. We may be the first and last. That's important. If you're looking for a hint as to how we should behave politically toward each other, toward our planet, then this idea matters. Imagine that the Earth is the only place in the galaxy where intelligent life exists, the only place where collections of atoms all this time have come together into improbable patterns that can think and feel and bring meaning to an otherwise meaningless universe. How should we behave? Surely, notwithstanding the fact that we are tiny, fragile things, and mote of dust orbiting around one star amongst 100 billion, we must consider ourselves and our world to be inconceivably valuable.